So in this integration, we're going to talk about how to build a stream data processing pipeline and how we did it for Nucleus for these integrations. We'll kind of talk about how to convert from batch data processing to streaming, because that's something we did for these integrations. Kind of go over the process of selection and adoption of new streaming technologies, and including Apache Flink, a database that we use called Rockset, and of course Apache Kafka, which is kind of the bones of a streaming pipeline. And we'll talk about some of the unique challenges that we had for this project, namely like taking data from a transactional database instead of like typical event streams. And then we'll wrap up with a demo. And again, I'm doing this talk at another conference, so some of these slides are going to be geared towards people who aren't familiar with, who don't know me and don't know community brands, so I can kind of skip through some of this stuff for the audience today. But for those who don't know me, my name's Kurt Buchter. I'm the product development manager for the Nucleus team. I think you guys all probably know community brands pretty well, so I'm going to skip over this one. And I think everyone's probably familiar with Nucleus, but just in general, Nucleus tries to provide analytics and insights for associations and nonprofits. Take data from various sources, combine it, and expose it through our easy-to-use web application. So, for example, take data from an AMS and event planning systems and stitch it all together and provide reporting analytics for it. So the goal of the project that we're going to talk about today, so for the goal to understand it, you kind of need to know a little bit of the history of Nucleus. When we were acquired by Community Brands back in 2001, it was kind of a standalone product. And then when we were acquired, we were tasked with becoming like the analytics provider for some of the other brands under Community Brands. And that's what we're going to talk about today. Your membership was that first integration, and then YM Careers kind of came right on the heels of that. But at the time we were acquired, we just had a couple dozen clients. The first product, Your Membership, has over 2,000 clients. This is a look of the before state of the Nucleus architecture. What we would do is take data from event planning systems or AMSs, bring data into our database and process the data with all the, perform all of our business logic down here, like in the batch processing pipeline. So again, we use batch. We had an Apache Spark-based batch processing system, and then we loaded data into an analytics database, and we use Apache Druid for that. From there, the data is kind of served to our web application through our web API. So some of this worked really well already and didn't need to be modified for the new integrations. But other things that other aspects of this, we kind of knew right away that the pieces that we had in place weren't going to work for these new integrations. One of those pieces is kind of right up here. How do we get data out of the source system? We had a custom-built tool that would sync data. We call it Cyclone. It syncs data specifically from SQL servers and brings data into Nucleus. We didn't feel like the existing Cyclone application we had was robust enough to handle these 2,000 client SaaS databases. So we just thought, it was a custom-built tool. It relied on some older SQL Server technology and put a little bit of load on the database, and just had some sync issues. So we kind of knew it wasn't going to be the right data sync tool for these new integrations. It worked well for a single tenant, smaller databases, but wasn't going to work well for YM and Careers. Another pain point was down here in batch processing. If anyone's familiar with, I know we got a lot of tech people here. If you think about a typical batch system, you might think, a job that runs once a day and maybe processes the last day's worth of activities, or maybe runs once an hour and processes the last hour of activities and kind of merges the the new data in with the full history. And that's not how our batch pipeline works. What we do is every time it runs, so maybe it's once an hour, once every couple hours, depending on how much data a client has, it's going to reprocess the full history of data. And there's good reasons for that. There's some complex business logic that needs to know the full history in order to make certain business decisions. But another reason, data is not immutable. Data changes, and when data changes, we need to reprocess a lot of things. So if a customer record changes, you kind of have to reprocess all the records it relates to. So there's good reason for why our batch processing pipeline works that way, but because of some of those reasons, it was slow and kind of costly, especially if we're looking at going from just a couple dozen clients to a couple thousand, and then kind of on the heels of that, a couple thousand more. So those are kind of the two pieces we identified up front that we needed to re-architect for the new integrations. So if batch is too slow and too costly, reprocessing data in batch is too expensive, then what's the answer? Well, stream processing is the answer, right? Here's a kind of an image of what a stream processing pipeline might look like. Excuse me. So we started researching like stream data processing pipelines. We had kind of a real-time or near real-time requirement for these integrations. As we started researching technologies, we landed on Apache Kafka as the streaming data platform. So that's right here in the middle. We settled on Kafka pretty quick because it worked really well with a lot of the other technologies that we were considering for this integration, that I'll get into here in a second. But the only other real player in the data streaming platform market is an AWS product, and Azure has one as well. But the other one that might have worked for us was AWS Kinesis. Since we're already using a lot of AWS, we're hosting everything on AWS. We considered that, but Kafka was really the right choice. It's open source. It's a lot more popular, more pre-built connectors. Good. Just in general, a really good choice there. So initially, when we started our pipeline, we hosted Apache Kafka in AWS with a managed service called MSK, which stands for Managed Streaming for Kafka. The next choice we kind of had to make was, again, I talked before about how our data sync application was not ideal for these integrations. So focusing on this step here, how are we going to get data out of source systems and into Kafka? So if you're not familiar with CDC, it stands for Change Data Capture. So what it does is monitors databases for any insert, updates, or delete statements, and stores those records in like a transaction log, or most newer databases or modern databases all have a CDC feature. So like in SQL Server, they store this data in a transaction log. MySQL uses a bin log. They all kind of have similar CDC features, but they're all pretty much the same. So CDC is kind of the technology there that we kind of landed on using. And then as far as we had a few options for implementing that. We could build something that looks at CDC on the tables and pulls the data out. So we have a lot of code to write to pull the data out, but there's also several like pre-built connectors that are ideal for this. And really at the time when we were doing the research, there's one called Debezium that kind of checked all the boxes for us. It worked well with Kafka, and one of the deciding factors is, it worked well with SQL Server. YM Careers and your membership both have SQL Server databases that we're getting the data out of. So Debezium worked well with SQL Server. and with Kafka. There's a few other options out there that work for other databases like MySQL or Postgres, but Debezium works well for SQL Server, but also supports some of those other databases. So by using Debezium and CDC, Debezium gives you like a full sync feature. So when you turn it on, it'll sync all the tables that you care about from the source system, load them into Kafka, and then once that initial sync is complete, it switches into CDC mode where it's just monitoring for ongoing inserts, updates, and deletes. The other decision we had to make was right up here, so the stream processing engine, we're going to call it. This is where the business logic's performed. We're taking data from several different tables, and we have to stitch it together, through joining. We did a lot of research on this. There's a lot of players in this space. For us, we narrowed it down to a couple options. One was an Apache Spark solution. So we already used, if you remember from earlier, we use Apache Kafka, or we use Apache Spark for our batch pipeline. Spark also has a streaming solution. So we researched that. And then another kind of up and coming technology is Apache Flink. So they're both Apache products, but Flink has a really active community. It's one of the most active Apache projects over the last few years. So ultimately, we did a proof of concept on both of those. They both seemed like they would check the boxes for us. So we did a full POC on both of them, and ultimately decided on Flink because of how well it handled state management. Our app would end up relying really heavily on state. If you remember earlier, I talked about how some of our business logic requires a full history of events to be able to make certain decisions. Again, like if you have to know a customer's all of their subscription history or membership dues history to be able to make a decision about, did this customer renew in 2017 or did they drop and rejoin or whatever. So because of that, we needed a good state management solution. And at the time we were doing this evaluation, Flink had a much better state management solution. Spark has had a solution, but it was like an in-memory only solution, whereas Flink uses a RocksDB based solution. And I think since we made the decision, Spark now has a RocksDB implementation, but I think we're still happy with our decision to choose Flink there. Okay, so after making those decisions, this was our proposed streaming data pipeline. Kind of starting from the beginning, you're pulling data out of a source database, which again is a SQL Server database for YM or YM careers. We get the data out of that with a Debezium connector and loads the data. And this is a update I need to make to the slide, but we started out using Amazon MSK for Kafka. The data would be processed in Apache Flink, and this is kind of an iterative process where we process data and then output it to another Kafka topic and then process it again, just based on how many layers or how many stages of processing you need, and then ultimately load the data into our analytics database, which again was Apache Druid. We had no reason at the time to replace Druid, so intended on using that, and then data is served up through our app by making queries to Druid. So implementation, we ended up having some issues with Debezium, just hosting it. The Flink implementation went pretty well. This is where we kind of spent the bulk of our development time, just building applications around Flink to get it to work with the rest of Nucleus. And we use the Python APIs in Flink, and we're using Flink SQL. It's one of the really cool things about Flink is that our old Spark-based batch pipeline uses a sort of a cryptic custom syntax to define joins and transformations, but our Flink pipeline now just uses Flink SQL, so we can create logic based on just using regular SQL, which is kind of the preferred language for data analysts. And then we did have some more issues with Druid. So we did not expect to have issues with Druid. Druid, we used it in our batch pipeline, but it also promised to, handle streaming ingestion very well. And I'll kind of talk a little bit more about streaming ingestion in a minute, but we didn't have issues with the streaming ingestion, but we had problems with Druid in that it doesn't handle database updates very well. It's not a excuse me. It doesn't handle mutable things, so things that can change. Something like Druid is, or like a ClickHouse or some of these other old analytics databases. They're great for streaming ingest. They're great for sub-second analytics queries, aggregating over millions of records and performing, those type of queries, but they're not as good at handling updates. So once a record is in Druid, you can't change it. So we spent a lot of time and effort trying to do some workarounds in here, trying to discover that data was updated, and back in the Flink pipeline, and trying to discover updates and it re-ingested into Druid. But anything that we came up with was kind of a clunky and expensive operation. So that led us to make a few changes. Because of these challenges, we pivoted to Confluent for hosting the Debezium connector. They have a managed version of that. We also use Confluent for Kafka itself. And then we ended up replacing Druid with a database called Rockset. The Druid challenges were really kind of a deal breaker for us. The workarounds we implemented didn't work for us. We ultimately needed an analytics database that was mutable and supported updates. So I discovered Rockset a couple years ago at this Kafka conference, and it could do everything that Druid could do as far as streaming ingest and fast querying, but it also supports updates. And so after implementing Rockset and Confluent, this is what the ultimate stream processing pipeline would look like for us. Starting up here with the partner databases, data comes in through Debezium into a Confluent cloud, or so Debezium is managed by Confluent Cloud. Data comes into a Kafka cluster and is reprocessed and back into Kafka a few times using Apache Flink, and then loaded into an analytics database, and we're going to use Rockset for, and then query it from our API or from our web app through our REST API. Okay, so if I didn't bore you enough there with the slides, I'm going to do a demo. All right, so to simulate the YM or YM Careers databases, I'm using an Azure SQL database here. And I'm going to try to do a full demo of all the technology that we just talked about. So, and try to do it from the very beginning. So I'm going to create a few tables here, and I'll talk about these in just a second. And what I'm doing here, so these queries are just enabling change data capture, CDC, for the tables we just created. And I'm going to insert just a bunch of data here. About almost 21,000 records I'm putting in across 5 different tables. And then let me okay. And this step takes a second or so, so I'm going to kick this off and then talk about the tables while this is running. So the tables I created, and this is just a subset of what you might, similar to what you would see for like your membership or any AMS. But I've got 5 tables. One is called tenants. This is basically, if we have 2,000 clients, each of them might have one record here. So this is like a multi-tenant database. There's a table for memberships. So anybody who's ever been a member gets a record on the membership table. For 5 years, they'd have 5 entries on the membership history table. Dues transactions is related to membership history, but holds like financial information. And then finally, we have the customer table, which anyone who has ever been a member is also a customer, but then anyone who's maybe attended events or anyone that a certain association is aware of is also on the customer table. So customer may not necessarily be a member. Okay, so looking back over here, I created this Confluent connector here. I'm going to flip to the Confluent UI. So this is Confluent Cloud. You can see that I created this connector. It's called Current 2023 Demo. You can see some of the settings. Got a password here that you don't need to worry about, but basically you just tell it how many tables you want to monitor. So I've got the 5 tables that we just set up, and then different settings for how to handle, numbers and like what data format you want to use, and how to handle like that initial load, whether you just want to load all the data from these tables, or if you just want to go straight into CDC mode. So just using the Confluent API to create this connector. So it looks like it's created. It still says 0 messages processed, but we'll go on here, and it shouldn't take too long for this data to come in. So the next step in our pipeline, so we've gotten the data. Once this kind of completes, we're going to get data from the SQL Server database into some Kafka topics. So if you're not familiar with Kafka, a topic is kind of like a table. It's just a way of separating data into different streams. So I think my session timed out, which is probably why I didn't see any messages processed here. Okay, so now I'm looking at topics here. These topics were all automatically created by this connector. Now we see we've got 26,000 messages already processed, and we can see data. Here's an example for customers. Just kind of show what some of the data looks like in here. Again, because this is using CDC or change data capture, it actually gives you a view of what the data looks like. And this is an initial load situation. But if we were to perform an update or a delete, it would show you what the record looked like before and then what the record looks like after. So looks like we've got most of the data is loaded already. So I'm going to go to the next step. The next step in our pipeline is the data processing. So we're using Apache Flink for that. I'm going to just manually create one topic here, and then I'm flipping over to a session for, this is using Amazon EMR. So EMR is just a service in AWS for managing applications like an Apache Flink or an Apache Spark. And I'm going to kick off this Flink job here. So I have a Python file with a bunch of Flink code in here. What this is going to do is take data from those Kafka topics and perform all of our business logic on it. So just kind of going over what we're doing. Again, we're using the Flink SQL APIs. So if you've ever done any database work like a DBA or created tables, altered tables, some of this logic looks familiar to you, as far as creating a table with a certain schema. But then everything down here is pretty Kafka specific, as far as like, hey, where is the Kafka cluster at? What kind of authentication do we want to use? What type of format is the data in? Credentials right here, username, password. And then there's a schema registry. So we've got some details about where to get the schema information from. So I've created one Flink table for each of the topics that we're pulling from: customers, dues, transactions, etc. And then I'm going to create a bunch of like in-memory tables. So these are kind of like views or just in-memory tables that run within Flink. So we've got one called membership history enriched, which is basically the job of joining all of the 5 tables together. Have another review called membership terms X months. And really what this is doing is just, if somebody's been a member for 12 months, it's going to expand that membership into 12 different rows, like one record for each month. And then we have our final table is called membership counts, which is just taking one record for each month and joining back to the original membership history enriched table to get all the demographic information like city, state, postal code, etc. And then ultimately, the data is going to be written back out to Kafka. So these 3 tables that we just created through select queries are all in memory, but then finally we're going to write the data back out to a Kafka topic called current 2023.membership counts. Flipping over here, you can see this is the Flink UI. This screen is the Yarn, which is the resource manager that we're using in Flink. Again, hosted in AWS's EMR service. But this here is the Flink UI. So it has created one job here for us. And again, this is really a small subset of everything that we would do for one of our YM or YM careers databases or integrations, but just enough to show the demo here. But this is pretty cool. I thought, Flink has a really cool web-based UI. They've created this job graph. You can see there's separate nodes here for every table that you're every source table or every source topic that you're pulling from, and then it has different nodes for like when you're performing a join. So this join is taking data from the membership history and the membership table and joining them together. And if you look at this job graph, it's not going to exactly look like the queries that we've run in here. So Flink just uses those and then sort of recreates the job graph in the best way it can logically do it. But then we have different outputs here. So it's showing you how many records were pulled in to each stage and how many records were output and everything. And ultimately, we end up with this output table, and that's going to be written back to Kafka. Okay, so the next step in the pipeline is loading data into our analytics database. So again, we're using Rockset for that. So I'm going to run this command using the Rockset API to create a new collection. So I'm going to call this collection current 2023 membership counts, and I'm going to tell it which Kafka topic it's coming from. This integration name, just an integration in Rockset, basically is a way to define the connection to a Kafka cluster and has your credentials and everything defined in there. And then it's pretty easy to create a new collection. I'll go over this field mapping query here in just a second. Now I'm going to flip over to the Rockset UI. So this is the website for our Rockset cluster, or our Rockset application. You can see here that this new collection just appeared. A collection is basically just a table or basically a table. So we have a new one that appeared here because I just ran the command. It's already connected, has 0 records ingested so far, but I think within a minute or so, we should see some data appearing in Rockset. Just a couple things here. This ingest transformation tab is going to look like this field mapping query. So what we're doing here is, again, I'll kind of go back to the Flink query where we created a kind of a primary key for the output, and I called it row ID. So Rockset has a couple special columns. One of them's ID, underscore ID, and one is underscore event time. So by using this, by setting our own primary key in this underscore ID column, Rockset knows that is the primary key, and that's how it handles the data updates. So whenever if a record comes in and it matches the ID of another record that already exists, it's going to update the existing record. And if a record comes in and it doesn't match another ID, it's going to go ahead and insert it. So that's what we call an upsert. So it knows if it should do an insert or an update each time a record comes in. I don't have to manually or even programmatically run an update statement. This is all just done through the streaming ingest. I kind of mentioned before, I'd talk a little bit about streaming ingest. This is how streaming ingestion works. You basically just tell Rockset, hey, I want you to monitor this Kafka topic, and it has all of the logic to pull records from that topic into its collection. This tab here just kind of shows you how far it is along processing all of the data in the topic and how close it is to being fully caught up. Okay, so starting with our source database, we've got data into our Kafka cluster through the Debezium connector. We've processed it a few times in Apache Flink, and then we've loaded it into a Rockset collection. So next I'm going to show some just how you query the data out of Rockset. This is just a typical select statement. Take that limit off of there. So just looking at all the data for a certain tenant. Again, we've got a multi-tenant database. This is going to be a multi-tenant Rockset collection as well. And look at data for a specific customer. So this customer, we can see, joined whatever association in 2013 as a student member. And looks like there's a little gap here. We're still waiting on Rockset to fully ingest everything. But once it's fully loaded, we won't have a gap here. But at some point, they became a full member, and so on. So let's see. I should be getting fairly close to all the data being loaded. At 70,000 records, and we should ultimately match this 255,000 records, because there were 255,000 records outputted from our Flink job. They should all ultimately end up in Rockset. And sometimes this screen lags a little bit, so just do a select. And we're at 81,000. Okay. Another example, I'll just kind of go on and hopefully that loads in the background. Here's a new tab here. This is more of what like an analytics query would look like. We're doing group bys and aggregations. This query is showing number of members per month for this specific tenant. So actually number of student members per month. So we can see, 2013, there's a row for every month. take this limit off again, all the way up through 2023. And this is something, you might think, well, why wouldn't I just run this query against the SQL server directly? If you add another filter here, or if I want to not just look at the count of total members, but I want to do a sum on the transaction amount, you can see that Rockset performs these queries, really fast. And for anyone who's done database programming or created a lot of queries, that when you have a database with tables with tens of millions or hundreds of millions of records, if you're going to perform this type of query on a database like that, you have to have indexes on all of these columns, right? Anything that you want to filter by, you have to have an index on. Anything you want to aggregate, you have to have indexes on, or it's going to perform very poorly. And one of the great things about Rockset is that it's indexed everything for you. You don't have to create specific indexes. If we look back here, I didn't create any certain indexes here. The only thing I did was create a primary key and a special event time column. So it just handles indexing everything for you. So I can group by or filter by or aggregate any column I want, and it's going to run really fast. Okay. Hopefully this catches up pretty soon, because the next part of the demo is going to rely on it. Let's flip back and run this one again. Okay, again, this is the same query that's looking at all the records for this customer. So we can see, looks like we don't have a gap in data anymore. So all that data has been ingested. So I've got 2013, 2014, 15, 16, 17. So it looks like we're getting pretty close. If I do a total count again, instead of step 20, 80, 85, 87,000. Okay. This query here is just looking at number of members for the specific association in the current month. So September 2023, number of members per country. This is kind of an example of something that Nucleus would run, these aggregations and these group by queries. Show me my number of members by month, or show me breakdown by country for the current month. So next thing I'm going to show, so this is all great. This works, this type of stuff could probably be performed, just with a data warehouse or even against the source system. But what happens when data changes, right? So that's the next step here. I'm going to go back to the source database. This is the customer record for customer 283, which is the same customer that we're looking at right here. We can see this customer lives in Albany, New York. And then we saw that we have 176 United States-based members. So what happens if I update this customer? Let's update them and set their country to Mexico. Okay, I'm going to open up a couple console windows here so we can show this a little bit better. And I'll explain these in just a second. Okay, I'm going to run this update again. So what this is showing here is this is basically just tailing one of the Kafka topics. So when data is recognized, we recognize an update from the source system. Our Debezium connector is going to pull that out of CDC and load it into this Kafka topic. And And then our Flink job is going to take over and recognize that this customer is linked to membership records and membership history records, and we'll see them flow back through here in Flink. Let's see here. Okay. I'm going to do this again. I'm going to update him to let's change his country to Canada. Okay. Bear with me here. So, okay, there it goes. It's going a little slow. All right, so right here, again, we're just looking for updates to this customer's topic. Here we can see a new record was produced into that Kafka topic, which is saying, all right, this operation was an update. Somebody updated this record in the source system. Here's what the record looked like before. And again, I know this is all smushed together, but then here's what the record looked like after. So it's hard to read, but you can see that before country said Mexico, and now country says Canada. Looking at the rest of these, on this window, I'm looking at our membership counts topic. So if we think back to our Flink job, Flink is taking data from this customer's topic, joining it with all of the membership history records and so on. And then, so what we see is the output here. Every record that customer was linked to now gets updated in this membership counts topic. So we look at country, we can see all of the records. So every month that this customer was a record, all got re-emitted through Flink and back into our output Kafka topic and updated that person's country to Canada. And then, so the next step, looks like Rockset is finally caught up here. Normally it goes a lot faster than this, but let's see if it's made it all the way in now. All right, that's good. So if you remember before, we had 176 United States members, and now we have one in Canada. So if I go back and run this query, seeing all the records for this customer, scroll over, I can see country is Canada for all these records. And again, one Canadian member. One more example here. So that's great. We can update customers' country. Let's show another example of updating a record from another table. Here's this customer's membership history record from January to December of 2013 or 2023. So I'm going to go ahead and delete that record. Let's say somebody made a mistake when they created it, and I'm going to reinsert a new record. So let's say when we first created it, we said they were a full member, and now we're going to change them to a senior member. Okay, again, watching our topics here, we see a new record emitted into the membership history table because we did a delete and an insert. It looks like it failed, but then again, everything that customer or that membership history record is linked to gets re-emitted through here. And this is one of the benefits that we get from using Flink. It's stored that customer record in state. It's storing these membership history records in state. So anytime that one of those records updates, it knows it needs to re-perform all of those joins. And again, those are all like in-memory joins. It doesn't have to re-pull data from the database. It's got it all in memory. So this time we expected to see not quite as many records changed because it wasn't just one customer record that changed, it was one membership history record. So we didn't have to update all the records from 2013 through 2022. We're just updating the records for 2023. So we saw about 12 records get re-emitted there. Again, they're going to use his new country, which is Canada, and have his new member type of senior member. See right here. So if we look back in Rockset, I can run another query here, basically the same as our group by country, but we're grouping by member type, and now we have one senior member. So that's pretty much it for the demo. I'm going to flip over here and show what it looks like when you put it all together. So if you can build a streaming data pipeline, with fast analytical queries and hook it up to your web application, this is what you get. Something easy to use for the end users who are not data analysts, who don't know SQL. Whenever we come in here, all these queries are going through our REST API and querying Rockset. So if I come in here and change a member type to just associate, it's going to rerun all these queries against the Rockset database. I can look for certain member types or certain years, or let me just show me joins instead of all rejoins or renewals. So again, this data is going, starting from source database. Anytime a record gets updated, it's going through Debezium, that Debezium connector into our Kafka cluster, processed by Flink, and then loaded into an analytics database, and then queried from that database through our web app and through our web API. So that's what I've got.